This is the 20th in a series of videos that I'm making to support a course in elementary number theory. And here we're going to talk about the index of a number with respect to a primitive root modulo n. Let's recall what a primitive root is first. So we say that r is a primitive root mod n if the order mod n of r is equal to phi of n. So in other words, this number achieves the greatest possible order mod n. Now that's equivalent to the following statement, and this is all happening mod n, even though it's not carefully written like that. That is that r to the k, as k runs through all the integers, mod n, is the same thing as the set of numbers between 1 and n that are relatively prime to n. So now let's look at the notion of the index, which is really like the discrete logarithm modulo n. So the index of a with respect to r, where r is a primitive root and a is relatively prime to n, I haven't written that there, but that's kind of the only way that makes this make sense, is the smallest non-negative integer k such that r to the k is congruent to a mod n. So here we could also write it like this. This is ind with a subscript r of a equals k. And we would read this as the index of a with respect to k, kind of keeping the understanding in the background that we're working mod n. Now let's notice that the values of k can only be between 0 and phi of n minus 1. That's because of this fact up here. Okay, so let's run through a couple of examples where we just look at some basic calculations. So I first want to notice that 2 is a primitive root mod 11, which means we can produce all of the numbers between 1 and 10 by just taking powers of 2. So let's do that. So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, but 16 mod 11 is the same thing as 5. 2 to the 5 is 10. 2 to the 6, well, that's going to be 2 times 10, which is 20. So that'll be 9 mod 11. And then we'll have 2 to the 7 is 18. That's the same thing as 7. Then we'll have 14, which is the same thing as 3. And then 2 times 3 is 6. And that finishes it all off. Notice we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are all of the numbers between 1 and 10, which is what we expect for a primitive root. But now this chart goes hand in hand with a bunch of facts involving the index. So notice that the index of 5 with respect to 2 will be equal to 4. And that's because 2 to the 4 is equal to 5 mod 11. Then furthermore, the index with respect to 2 of 7 will be equal to 7. That's because 2 to the 7 is the same thing as 7. Then we can really just keep going. So notice that the index with respect to 2 of 10 is going to be 5. That's because 2 to the 5 is 10 mod 11. So we can in fact create an entire chart, which is maybe dual to the chart that we have on the board with facts like this involving the index instead of powers of 2. So let's look at another kind of symmetric example or parallel example to this. So 3 is a primitive root mod 10. So notice 10 is 2 times a prime, so we know that it has a primitive root. In fact, 3 is a primitive root. So let's calculate powers of 3. Phi of 10 is only 4, so we only need to look for 4 numbers here. So 3 to the 0 is 1, 3 to the 1 is equal to 3, 3 squared is 9, then 3 cubed is 27, but that is 7 mod 10. So there we have that, but now we could write that the index of 7 with respect to 3 is 3. That's because of this entry in the chart. And then furthermore, the index of 1 with respect to 3 is 0. That's because 3 to the 0 is 1. And then notice these also give us, similar statements that we could write down about the index. So now that we've looked at some examples, kind of getting an idea for how the index works, let's prove a nice result that draws a parallel between the index and the logarithm. So let's look at this theorem that really draws a nice parallel between the index and the logarithm. So the first is that the index of a times b is equal to the index of a plus the index of b mod phi of n. The next is that the index of 1 is equal to 0. The next is the index with respect to r is equal to 1. Then next, we've got some sort of exponent rule. The index of a to the m is equal to m times the index of a mod phi of n. And then finally, the index of -1 is phi of n over 2. So notice if we just replace index with logarithm, all of these things hold over appropriate real numbers. So that's kind of interesting. And in fact, the proofs are going to go pretty much the same. So I won't prove all of these. So notice the proof of the index of 1 being equal to 0 is pretty obvious, because if you've got a primitive root r, then r to the 0 is equal to 1. And then furthermore, that the index of r is 1, that's also pretty obvious. So let's see, maybe we'll prove 1, 4, and 5, because those are the ones that require a little bit of work. So let's start with 1. And I guess I should say in the background here is that r will be our primitive root, and then a and b are relatively primed to n. So here, let's write a as r to the k mod n, and then we'll write b as r to the l mod n. So we know that's possible because r is a primitive root. But now the calculation is pretty straightforward. We have the index of ab is the same thing as the index of r to the k plus l using exponent rules. But notice that that will be congruent to k plus l mod phi of n, just by the definition of the index. But that's exactly equal to the index of a plus the index of b mod phi of n, which is exactly what we want for this first case. Okay, so now let's maybe move on to the fourth, which will have a pretty similar proof. So let's suppose that a is congruent to r to the k modulo n. And then we'll calculate the index of a to the m. Notice that's the same thing as the index of r to the mk, again by exponent rules, but that's exactly equal to mk modulo phi of n by the definition of the index. But then k is the index of a, so we can just make that replacement. This is m times the index of a mod phi of n, where again, this k is the index of a by this fact right here. Okay, so we've proved 1 and 4. Let's maybe get rid of those and we'll prove 5. Now we're ready to look at a proof of this fifth statement, which I think by far is the trickiest of all of these proofs, some of which we're obviously skipping. So let's start by introducing some notation. So let's maybe set k equal to the index of -1. So we really want k to be phi of n over 2. So notice that if k is the index of -1, that's the same thing as saying that r to the k is congruent to -1 mod n. And k is the least non-negative number that makes that happen from this definition right here. So now we'll make the following string of arguments. We'll take 1 and we'll read it and rewrite it as -1 squared. But now we'll take this -1 and write it as r to the k. So this is the same thing as r to the k squared. We're working mod n. This first was just equality in the integers, but now this is congruence mod n. So next we'll use exponent rules to see that this is the same thing as r to the 2k mod n. But let's look at the equation that we have here. We have r to the 2k is congruent to 1 modulo n. But now we can take this 1 and write it as r to the 0. And then extract the exponents. So we know if that bases are congruent mod n, then the exponents are congruent mod phi of n. So this tells us that 2 times k is congruent to 0 modulo phi of n. But let's see what we've got now. That tells us that 2k is a multiple of phi of n. So that means it comes from the following set. We have 2k comes from the set phi of n, 2 times phi of n, 3 times phi of n, and then so on and so forth. You might say, well, how do we know that it's not 0 times phi of n? That seems like it could be a possibility. But given that k is the index of -1, we know that it's not 0. But keeping that in mind, we know that from this definition of the index and this kind of thing that we noticed before, we see that k comes from the set 0, 1, 2, all the way up to phi of n minus 1. But putting these two facts together, the fact that 2 times k comes from this set and k comes from this set, that really means that 2 times k can only be equal to phi of n. If 2 times k was equal to 2 phi of n, that means k would be phi of n, but that's outside of the set determined by this definition over here. The same thing would be true for all of these afterwards. So just to reiterate, we know that 2 times k is equal to phi of n, but that tells us that k is equal to phi of n over 2. But rewriting that with the fact that k is the index of -1, that achieves this fifth equation that we wanted right here. You might be a little bit worried because we're dividing by 2, but let's recall that phi of n is even unless n is equal to 1 or 2. So this kind of thing works for all numbers bigger than or equal to 3. So we're going to finish this video off by proving that powers of 2 almost have primitive roots. We proved that they did not have primitive roots in a previous video, but here we'll show that they come pretty close to having primitive roots. So let's recall that there is a primitive root mod n if n comes from the following set of numbers. So it can be equal to 1, 2, 4, p to the k, or 2 times p to the k, where p is an odd prime. So let's notice that maybe the most glaring thing missing from this list would be powers of 2. So why are powers of odd primes okay, but powers of 2 are not okay? In other words, they don't give us the possibility of primitive roots, even though 2 is a prime. Well, we saw why that was the case in the proof of this theorem, which was a couple of videos back. And here we want to show that we almost get primitive roots if we're working mod a power of 2. And in fact, we'll do this in a very constructive way, and we'll show that this following set is a reduced residue system mod 2 to the n. So we've got plus minus 5 squared, plus minus 5 cubed, all the way up to plus minus 5 to the 2n minus 2. So if you think about having a primitive root as being generated by that primitive root and only generated by a single element, here we're generated by 2 elements. One element would be the number 5, and the other element would be the number -1. Because notice we can gain everything on this list by multiplying by 5 and -1. So let's maybe get into this proof. So let's first notice that this set has the correct number of elements. And we can do that by calculating phi of 2 to the n and seeing that that is equal to 2 to the n minus 2 to the n minus 1 by a thing that we showed before regarding the Euler phi function. But that's equal to 2 to the n minus 1. But that's exactly equal to 2 times 2 to the n minus 2. And how many guys are there on this list? Well, there are exactly 2 times 2 to the n minus 2. We have plus minus this, plus minus this, plus minus this, all the way up to plus minus this. Here we've got an exponent of 1, 2, 3, all the way up to 2 to the n minus 2. So we've got 2 choices for each of these 2 to the n minus 2 spots, giving us 2 times 2 to the n minus 2 total choices. Again, to reiterate, we have enough elements. So what's left to show is that these are all incongruent. So plus minus 5 squared, all the way up to plus minus 5 to the 2 to the n minus 2 are incongruent mod 2 to the n. Okay, so we have to start somewhere, and where we'll start is, instead of looking at the entire set, we'll look at just the set of the positive powers of 5. So first, we'll look at 5 squared, 5 cubed, all the way up to 5 to the 2n minus 2, and we'll show that these are actually incongruent mod 2 to the n. But notice that that is equivalent to finding the order mod 2 to the n of 5 and getting 2 to the n minus 2. So just to reiterate, this is our first goal, is to show that the order of 5 mod 2 to the n is 2 to the n minus 2. So let's jump into that. So we know off the bat that the order mod 2 to the n of 5 divides 2 to the n minus 1. Well, that's phi of 2 to the n. Well, that's because the order of an element always divides phi of whatever we're working mod. So that follows from this. But we also know that there's no primitive root mod 2 to the n. So in fact, the order is not guaranteed to only divide this, but it will also divide this divided by 2. So in other words, we have the order mod 2 to the n of 5 divides 2 to the n minus 2. Again, that's because there's no primitive roots mod 2 to the n. So the largest order that we could have is not phi of 2 to the n, but it's phi of 2 to the n over 2. Okay, and now we're going to claim that we actually achieve this order. So I'll write that here. So we want to claim for all n bigger than or equal to 3, the order mod 2 to the n of 5 is equal to 2 to the n minus 2. Well, why n bigger than or equal to 3? Because if n is equal to 1 or 2, then we actually have a primitive root, so we're not in this setup in the first place. But now let's notice that the order mod 2 to the n of 5 is equal to 2 to the n minus 2 if and only if we have the following divisibility property, and that is 2 to the n divides perfectly in 5 to the 2 to the n minus 2 minus 1. Remember, we can use this double divisibility sign to say that 2 to the n divides into this, but no other powers of 2 or no larger powers of 2 will divide into this. And so this is actually what we'll show by induction, and we'll do that maybe on the next board. We're at the stage of the proof that we want to show that 2 to the n is the largest power of 2 that will divide into 5 to the 2 to the n minus 2 minus 1 for all n bigger than or equal to 3, and we'll do this by induction. So let's see what our base case will be. So since we're looking at only the cases when n is bigger than or equal to 3, our base case will be the n equals 3 case. So in that setup, we'll have 5 to the 2 to the 3 minus 1, but that's 5 squared, which is equal to 25 minus 1. So that's going to be equal to 24, which is equal to 8 times 3. But notice that 8 is equal to 2 cubed. And yes, we have 2 cubed is the largest power of 2 that divides into 5 squared minus 1. So we're good to go in this case. Now let's make an induction hypothesis. So that'll be so let's suppose for some k bigger than or equal to 3, we have 2 to the k is the largest power of 2 that divides into 5 to the 2 to the k minus 2 minus 1. And then consider the k plus first case. But the k plus first case in this object will be 5 to the 2 to the k minus 1 minus 1. But now that's in fact a difference of squares. It's a little bit tricky to see that it's a difference of squares, but let's notice that it is 5 to the 2 to the k minus 2 squared minus 1. So the exponent rules are a bit tricky there, but if you write it down carefully, you'll see that that works out. That means we can factor that as 5 to the 2 to the k minus 2 minus 1 times 5 to the 2 to the k minus 2 plus 1. And now notice by our induction hypothesis, this guy right here is equal to 2 to the k times an odd number. We know it's equal to 2 to the k times an odd number because 2 to the k is the largest power of 2 that divides into that. Then we can easily see that this guy right here, 5 to the 2 to the k minus 2 plus 1, is congruent to 2 modulo 4. Just reduce that thing mod 4. 5 is 1 mod 4. You've got 1 plus 1, which is 2. But everything that's 2 mod 4 is equal to 2 times some odd number. That's a defining characteristic of things that are congruent to 2 mod 4. But now putting this thing in light green and this thing in yellow together, we see that this object right here is equal to 2 to the k plus 1 times some odd number, which is the product of that green and yellow odd number. But that's exactly the same thing as saying that 2 to the k plus 1 is the largest power of 2 that divides into 5 to the 2k minus 1 minus 1. And so we've proved this claim. And so let's see where that gets us. So let's see what we've got so far. We just got done showing that every element in this set, the positive powers of 5, so 5, 5 squared, 5 cubed, up to 5 to the 2n minus 2, are all incongruent mod 2 to the n. From there, it's pretty obvious that all of these numbers, minus 5 squared, up to minus 5 to the 2 to the n minus 2, are also incongruent mod 2 to the n. That's because we're taking all of these and multiplying by something whose GCD with 2 to the n is 1. Just think back to the proof of like Euler's generalization of Fermat's little theorem, and we do something like that. So in conclusion, or in midpoint conclusion, these two sets contain elements that are independently congruent within the set. Now what we want to show is that it's impossible for something from this set to be congruent to something from this set. That means that if we smash these two sets together, we have a set of all reduced residues mod 2 to the n. Again, because we have the right number. Okay, so let's do that by way of contradiction. So we'll suppose 5 to the x is congruent to minus 5 to the y mod 2 to the n. So notice 5 to the x comes from that set, if we let x come from the correct range. And then 5 to the y comes from that set, again, if we let y come from the correct range. That tells us that 5 to the x plus 5 to the y is congruent to 0 modulo 2 to the n. But next, we want to notice that in our current setup, n is bigger than or equal to 3. So we have 5 to the x plus 5 to the y is congruent to a power of n which is bigger than or equal to 3. That means it's congruent to 0 mod 8 or 16 or 32, so on and so forth. That means that it must be congruent to 0 mod 4. So if you're congruent to 0 mod 8, in other words, if you're a multiple of 8, then you're automatically a multiple of 4. And furthermore, if you're a multiple of 2 to the n, or n is bigger than or equal to 3, then you're already a multiple of 4. But now let's, on the other hand, just reduce this equation mod 4 using plain old modular arithmetic. So 5 to the x plus 5 to the y is congruent to 1 to the x plus 1 to the y, which is congruent to 2 mod 4. So that gives us a contradiction because 2 is not congruent to 0 mod 4. So what did we contradict? Well, we contradicted the ability of somebody from this set to be congruent to someone from this set. So that finishes our proof because not only are elements from this incongruent with each other and elements from this set incongruent with each other, but elements from either set with the other set are also incongruent to each other. So we're done proving this theorem. So let's finish off with maybe a quick warm-up exercise that you could do based on this information. So I've got a quick warm-up problem. So working mod 23, find the index of 21 with respect to 5 and the index of 7 with respect to 5. And then if you're in the class, you don't really have to worry about this because we're going to be doing this in class. But I'm sure a bunch of you guys watching this are not in my course because there are only like 8 students in the course and thousands of people watch these videos. I think this is a nice kind of exploratory exercise where you build the notion of an index to things going mod 2 to the n. So I'll outline this right here, but like I said, we'll be doing this as a group exercise in class. So working mod 2 to the n, we can find the index of A, mod 2 to the n, is equal to KL. So it's an ordered pair. A is congruent to -1 to the K, 5 to the L, mod 2 to the n. So here we have K comes between 0 and 1, and L goes between 1 and 2 to the n minus 2. So that's built off of this last theorem that we proved that said all of the reduced residues mod 2 to the n are plus minus 5 squared, and so on and so forth. So this further generalizes the notion of a primitive root. So what's the game here? So you want to develop a theorem that's similar to the one at the beginning of the video involving the index of products, the index of a power, and then so on and so forth. Okay, so that's a good place to stop.